Alrighty. Excuse me. Alrighty, folks. We are starting the third and final chapter of this PowerPoint. And if you think this one is long, I'm not even sure how many slides this one is. Let's see here. 60. That's not too bad. If you think this one is long, I had a 90-some slide presentation on evolution. That was long. You guys don't get that, though. Yeah, what a shame, huh? So, switching gears yet again to talk about something else that is fairly important when you want to learn about the Earth. You need to have a rough idea how long it's been here doing its thing. All right? And that allows us. You may wonder why we're looking at other planets. It's not just for their resources. It's not just for, for their resources. But we can learn a lot of stuff about ourselves by looking at how other planets have changed. You'll learn one of our vocabulary words today, a new theory we're going to introduce that maybe sheds a little light on why we do care what's going on Mars and so on and so forth. So, if you didn't know, the Earth is right around 4.5 billion years old, 4.6. There is another decimal if you care to go that far, but we don't need to. Well, there we go. I guess we did. It is 4.54. And I don't know why I rounded up to 4.6, but I did. And that's based on the age of a meteorite. Now that right there gives some folks a reason to pause. They're like, well, why are we dating a meteorite? Why don't we just date the Earth? Well, there's a handful of reasons for that. For one thing, bless you, you've got sedimentary rocks everywhere. All right? And it's like a layer of dust that's been gathering for 4.5 billion years. Now, mind you, every so often we sweep or vacuum or dust or whatever you want to call it. Nature, takes care of stuff like that. But it is literally sort of the old saying, needle in a haystack, trying to find rocks that are that old, of course, without, drilling through all of the sedimentary rock that's there. And even then, there's a lot of things that get in the way. You might be thinking, well, wait a minute, sedimentary rocks are made up of old rocks. I remember that from our science class in high school. You're absolutely right, but again, you're even now more diluted. Okay, you've got, we'll just make up a number, 500 different pieces of sediment inside any given sedimentary rock, and each one of them potentially is from a different parent rock, a different age, so on and so forth. It's tough. We have found on Earth, I want to say we're right around in the 4.3. So this 4.6 that we're talking about is not by any means out of the ballpark. Right church, pretty dang close to the right pew. So why can we use a meteor? Well, we have something called the solar nebula theory that we're going to talk about that tells us that and I'll get into details on this, more or less everything in the solar system is about the same age. I'm using a lot of vague terms on purpose, okay? Because it wasn't a magic wand waved, poof, there's a solar system. All right, it took time to grow, time to organize itself, so on and so forth. But compared to all the other stuff out there, it's essentially the same age. It's like maybe the kids on your block that you grew up playing with, okay? You were all 13. Well, maybe one of you was born in September, one of you was born in July, But you're all essentially the same. It's the same idea, except with a much bigger fudge factor there. I'm really bummed. I had an opportunity to go here this past summer, and because I've been using this or a similar slide for a very long time. The first meteorite we tested was from the Barringer crater. All right, the Canyon Diablo meteorite, as it's called. And it landed here about 50,000 years ago, from what they can tell. That's the crater, by the way. And if you are looking just, we'll call it to the lower left, you see that brown splotch there and what looks like a stream coming in. That's the visitor center and a road coming in. It's a pretty big hole. We were just out there with scouts and touring around all the touristy spots, but unfortunately, this is privately owned. And it is as tourist trappy and UFO alien-y, which again isn't a bad thing, as you could imagine. And unfortunately, we were traveling with about 30 people, and $45 to $50 a head they wanted to get in was unattainable for us. And so I did not go see it, but I saw a lot of other cool things out there this summer. But this is one I would have liked to see. That is a hunk of the meteorite down there. And another thing, we talked about how everyone uses speed and velocity and mass and weight interchangeably. And I go and I use meteor or meteorite and asteroid and a couple other words loosely, and you guys all jump all over my case. So yeah, I do know the difference. We don't need to get into the difference in here, all right? But it's not like I'm calling it a comet or anything, okay? Comets are completely and utterly different. So I know I say asteroid, and I know I say meteor, and I probably refer to it as a meteorite, but you get the idea. So that was the first of many that we've dated. And they've all come in, again, right around the same date. We've also now sent our little droids out into space. And we've sampled stuff from out there. And they all come around the same date. We've been on Mars. We've sampled that. Same date. So, you wonder perhaps why this solar nebula thing isn't a hypothesis and why it got bumped up to theory, and going back to what little bit we talked about the scientific method. We've got a decent amount of data that says this is what's going on. So what is it? So what we're putting forward is the idea that our sun and everything around it formed out of something called a nebula. We'll explain what a nebula is in a minute. And little by little, everything formed. A nebula is a cloud of gas and dust. It is both the beginning and the ending of a star. I hate to go back to gravity, but it's all a function of gravity. These nebulas are literally, you've seen, and I hopefully have a picture of a nebula coming up here. These giant, they're really cool. If you're ever bored on the internet, Google some pictures of nebula. Cat's Eye Nebula, there's a Crab Nebula, there's a handful, an Eagle Nebula. They don't look anything like, they're worse than constellations. Some of them, the cat's eye actually looks like a cat's eye, I guess. But you'd be hard-pressed to see an eagle, I think, in the Eagle Nebula. At any rate, so it is just gases and particle pieces, parts. We say dust. But what happens is as they're moving around, eventually they're going to start bumping into one another and sticking together. All right, and this is where gravity kicks in. Once you get a couple pieces together, they're that much more likely for something to be attracted to them, or vice versa, for them to be attracted to something slightly bigger. And it just builds and builds and builds and builds. All right. There's a word for it. You don't need to worry about it. I don't think it shows up on a slide, called accretion, HCC, and that's planet building. All right, at least for the rocky planets. And I'm getting ahead of my slides here, but I'm on a roll, so I'm going to stay with it. This explains the layout of the planets as well. We have the rocky planets closest to the sun. We have the gaseous planets farther away from the sun. Again, the sun is our huge center of mass in our solar system, right? So the stuff that has more mass, the solid material, these rocky inner planets, were more attracted to it. They were not able to escape as easy as the lighter gases were. So it's a heck of an idea. So it's also the end of a star, because you've heard of supernova, right? When a star explodes, well, that's what it leaves behind. And again, whether or not it gets a slide in a couple minutes, I give this cosmology conversation so many times that even though you're not technically getting the cosmology talk this semester, I can't help but relate a couple related ideas here. This is how we fuse elements, okay? Hydrogen to helium, is typically what a star does. As we go through the star's life cycle, it fuses higher and higher and higher elements. It can only fuse up to iron before it starts to collapse. Iron's pretty heavy stuff. Maybe that has to do with it. I don't know that much about nuclear physics and or chemistry, but I do know it gets to iron, and that kind of makes sense. However, once it collapses and explodes, the energy that creates is like way beyond what was happening in the star before it exploded. And through that energy, we fuse the higher elements little by little. Okay, you might have heard of first generation stars, second generation stars, so on and so forth. Okay, so slowly but surely, as the universe is building more and more elements. So, anywho, lest I digress. So, what is a solar system? A solar system is an area around a star. In our case, the star is the sun. The sun is a star, guys. When I ask you what the closest star is, please say the sun. And that includes planets, dwarf planets, asteroids, comets, and moons. Okay, that's what's in a solar system. Once they demoted Pluto, probably aware of that, they found a handful of other, well, they didn't find, the people who found it a long time ago started going, well, there's also this guy, and this guy, and this guy. So our list of dwarf planets grew rather quickly, that we acknowledge. Many of them are bigger than Pluto, even. So dwarf planets is definitely a thing. Just diametrically challenged, really. Nothing more. But in the asteroid belt, okay, talk about asteroids, is right in between the inner and the outer planets. Again, that makes sense. You've got your rocky terrestrial planets, and you've got a whole bunch of debris, and then we fade into the gaseous planets. They're either planets that came together and got destroyed along the way, or stuff that just never fully accreted, and gravity just sort of put them into a spin like all the satellites around us. And there they remain for all of our cool star pilots that fly through in all of our sci-fi movies. There is a nebula. You see the crab? No. I mean, it's roughly crab-shaped if you remove all of its arms and legs and so on and so forth. But so there's an example of a nebula. And like I said, they're very cool things. This one happens to be in Taurus, the constellation, which is about 6,500 light years away. Again, it's eluding me this morning on whether or not we get into a slide that has a conversation about light years on it. But light years was one of the questions in your very first labs that we did. All right, when we had you tossing around all of those little factoids and constants and vocabulary words and whatnots. So Let's see. We do have that way. I don't. Oh, you know what? I'm just going to stick to my dang slides. I mentioned the word supernova a moment ago. So a supernova is an exploding star, leaves a nebula behind, and as I indicated, it does allow us to fuse beyond the element iron. What do I mean by beyond? Well, remember that periodic table we mentioned briefly a long time ago? What, 3 weeks now? All right. Those. They're in order of increasing protons. Remember that? We're coming up on a test here pretty soon, so you want to remember that. So, elements beyond iron. So supernova is a stellar explosion. What's another way a star can die? Who knows one? There's a couple cool ways. See, rattling off things on your hand. You got 3 or 4 left?
Oh, I was trying to remember.
You know, it's a famous one. Everyone you'll say, "Oh yeah, I knew that." Well, that's that one. It is the Black hole. There you go. It can do the opposite of exploding. It can implode. All right. Collapses in on itself, goes to a black hole. That's another way that a star can die. And those are relevant, for lack of a better word, because arguably at the center of at least every spiral galaxy, there's one big old black hole in the middle there. So we've got a black hole nearby. All right. But galactically speaking, nearby. All right, so these pictures in the background, this is a really nice illustration. It kind of shows you what I said a couple minutes ago about, and I'm going to go into more detail now, about how stuff clumps up. Okay, I used the word accretion, remember that? And we told you that little particles bang into one another, get stuck, and they're that much more likely to pull more particles into them, and so on and so forth. So you might wonder how that gets rotating or spinning, because of course the planets are revolving around the sun. All right, our galaxy is rotating, it's spinning, whatever word you want to use. How does all that happen, and why is it flat? If we had a big old ball of gas or some strange random shape, why do we now look like a hubcap? All great questions. And 2 reasons. Centrifugal force and conservation of angular momentum. You do not need to remember those words for a test, but you do know them. Okay? Was spin art still a thing when you guys were growing up, when you were kids?
Yep.
I see a couple no's, a couple yeses. So depending on where you went. It used to be a thing you do at home. Then it moved to like fairs and festivals. Basically, you'd put some paint on a piece of paper in the center, and it was on some sort of turntable thing. You spin it really fast, the paint goes off in all directions. Okay, that is what spin art was. Okay, you guys know it more. You have a less likely chance, but you've seen it on TV, of being on a merry-go-round. All right, there's a reason they banned merry-go-rounds. They were lots of fun. And there's still, not like they used to make them. There's some interesting new modern versions. There was one right in, not Proctor Park, but the Parkway Park there. There was some version of a merry-go-round as well. But no, good old-fashioned metal disc on an axle, with metal bars going around it that you were supposed to hold on to.
Oh, you mean the playground thing, yeah.
Yeah, not a carousel. Not a carousel, a merry-go-round. Okay, when my kids were growing up, we were hard-pressed to find them. You find a few. I've seen even a metal slide here or there. But, so, good. So you guys know what we're talking about. So the idea is, of course, that if the teachers had their way, the merry-go-round comes to a stop, everyone gets on, and the people that are already on there, everyone gets off, and then we spin it around and around and around. Well, that's not what we used to do in the 80s, of course. We were supposed to, but the teachers were too busy having a smoke break to pay attention to us. So we would jump on while it was moving, we'd jump off while it was moving, and yeah, occasionally somebody would get hurt, but that was, it was recess. That's what recess was for. Well, what we were too young to notice was that as we jumped on, for that brief moment or two, that merry-go-round went a little quicker. Every time someone would jump on and manage to catch a hold of that bar, they would add their force going forward, and it would keep it spinning. That's that conservation of angular momentum. All right? Everybody just flies off. Everyone jumps on and keeps it spinning. So when these things are bumping into one another, it creates a rotation, okay, in this nebula, this cloud of gas we were talking about. Then, centrifugal force kicks in. It's time to get off the merry-go-round for whatever reason. What did we do? Well, we would let go and go, wah, like Spider-Man and fly backwards, okay? Yeah? If they were smart, they moved all the trees out of the way for us already. But yeah, you might hit a tree. You might land on a rock. You might land on a friend. You never knew. But again, we didn't care. It was fun. So that is the centrifugal force, okay? You guys know it probably quite better now if you've ever been on Gravitron, I think is the name of the most common one at the fair, okay? Spins around really, really quick. They drop the floor out. You stay stuck to the wall. That is probably the worst ride to go on at any festival or like movable fair kind of place, because that depends entirely on that machine working really well.
The best one around here is the Darien Lake. They still have
Okay. Well, that's, like I said, that's permanent, for lack of a better word. That one, I'm talking, you go into this church festival or something.
Yeah, they're a little sketchy.
Because if that thing slows down, your level of centrifugal force drops and you fall into the gears and stuff, and not good. So we need that rotational force, and that spreads out these things. All right? So we have all these pieces, parts banging into one another. That gets it rotating. And then as it rotates, it starts to spread out. So that's how we form a disk. Okay? And that's what they're showing you here in these images. Now, all that stuff that's in the nebula, the majority of it stays in the center. By far, they'll tell you that hydrogen is the most common element in the solar system. All right? And that's good because we need it to make stars. All right? So 90% of the material stays in the center and forms a star. It's worth pointing out that this isn't just us that has a solar system. Okay? Any star out there has the potential to have a solar system around it. We're finding more and more planets all the time. So this process isn't just one time for us right here. We're special, but we're not that special. Okay? So this could potentially happen around any star. So the remaining 10%, the riffraff that's floating around that didn't get condensed into the center there, spins around and essentially goes through that same process that we call accretion. I'm sorry, my watch is going nuts for some reason. So while the solar nebula theory is important because it describes how we're pretty sure our solar system formed and other solar systems, the application of it is, in our conversation at least, way, way more important. And that application is that, again, everything around us is approximately the same age. 4.5 billion years. And why we care, to get back to the point, is that we could look out one planet. Don't worry, I'm not going to make you guys memorize the order of the planets, because I get lost even after the asteroid belt. I always forget whether it's Jupiter or Saturn that comes first, and so on. So we don't need to do that. Earth science folks, they will need to do that, but not in geology. Anywho, we look just past us at Mars. We look just inwards one planet at Venus and realize that they're brothers and sisters, essentially. And say, oh my God, Mars, what happened to you? Oh my gosh, Venus, wow, you're way different. And using the fact that we know they approximately have the same birth date, that's one less variable that we have to contend with. Venus is a good bit closer to the sun. It's very similar to our diameter, but closer to the sun. And, okay, now how is it so different? You look at Mars. Mars is a decent amount smaller than us, and it's farther away from the sun. And, oh my gosh, it's so different. So it allows a lot of comparing and contrasting and projection. Okay? This one is, like I said, smaller and farther away. We know now we've got little droids driving around on it. We're seeing old riverbeds. We're seeing sedimentary rocks. We're seeing all this stuff that tells us that at least at some point Mars looked more or less like this. Don't know that they got through the whole evolution thing. All right? At least they haven't told us that they've found plant fossils and tree fossils and all that stuff yet. But it did have a surface with flowing water and ice. Venus is a little tougher. Venus has one hell of an atmosphere. Okay? And the surface of it, we have seen little bits and pieces. I think that the cameras essentially end up getting destroyed really quickly, and or they can't see very far. Or maybe both. But again, we certainly understand its atmosphere. You always hear runaway greenhouse effect when they talk about Venus. It's just an appropriation of terms, but the idea is similar. So it allows us to learn about the other planets. All right, so that's a really neat application.
Thinking about, because the atmosphere can't really pass below it at one point, but it's up high. Well, I guess not high, but low enough that they have like an unmanned airship plan kind of mission.
For Venus?
Yeah.
I haven't heard that one. But unmanned, that I can believe. Yeah. That I can believe. Yeah, we've got to go explore. We don't go that way that often. Yeah, I'm much more interested in Mars. We could terraform that, and so we think at any rate. But we'll see. As long as we live under a dome, which is mixed, that would kind of stink, I think. But a lot of people lined up around the block when they did that whole join our mission to Mars thing. I don't know whatever happened to that. That was a good 10 years ago. But they probably sent them out to Utah, and half of them freaked out and left the program, and so on and so forth. But at any rate, yeah, we seem to be much more interested in Mars, and understandably, as we just discussed, it's a lot easier to make that work. And we will be there fairly soon. We're going to go back to the moon first, I believe is the order, and then we're going to build a station there to get us to help us get to Mars a little easier. It takes about 3 months to get to Mars, if I remember correctly. So it's a bit bigger of an adventure. All right. For those of you wondering what we've been talking about, Mars and Venus are other planets in our solar system. Yeah. We are third rock from the sun. Used to be a sitcom. Even that, though, was stolen from a much better song, Third Stone from the Sun, Jimi Hendrix. But yeah, that's Earth, okay? What's the first one there? Mercury, good. Then we go to Venus, then us, then Mars, and now the answer's clear to me. Who's next? Jupiter. See, as I said, I always mix up Jupiter and Saturn. Saturn's got the rings, though. All right, so then we get out to our gaseous and way out there. See that little dot? That's not a moon circling everything. That is poor old demoted Pluto. All right. But as I said, there's other planetoids out there, dwarf planets. I shouldn't say planetoids. Dwarf planets out there that are apparently a good bit bigger than Pluto. Ceres comes to mind. I used to know another one. So there's more of those out there. I don't know that we'll ever include them in our diagrams. All right. Oh, there you go. There you go. If they have resources we want, or little green people on them or something. But so we are now 8 planets, okay? Don't miss that on the test. 8 planets plus Pluto, etc. It's no longer 9 planets. It hasn't been 9 planets possibly since you guys have been alive. It's been a while. It's been a while. We're not going to get into rotation and elliptical orbits. All again, Earth science folks are going to have a whole section. I'm talking to them because they share this lecture with you guys. You guys in your astronomy section are going to learn all about this. In geology, we don't, which is where I'm talking to right now. We don't get into this too much. 2006. You guys were arguably just coming into this world around then, probably.
I was 10.
Okay. Oh, well, there you go. All right. 4.5 billion years ago, the material that our Earth is made of coalesced in space. We use the term accretion. This material was elements, okay? We're made of elements. And we had this lovely molten ball of elemental stew, as I like to say. It was held together by gravity. And as you probably noticed, it is no longer a fiery molten ball. It did cool off. We have a crust, which we mentioned in the previous section. And as you may or may not have noticed, probably just from the news, but every so often it leaks, so it's not entirely cooled off. We've got magma coming to the surface as lava coming out of a volcano or some other big crack or crevice. This is a great picture. And it does kind of look like a marshmallow. You've heated your marshmallow way too much. I've seen the black, but I've never seen the molten red in my marshmallows. But at any rate, the red is obviously where it's still hot. The black is where it's starting to cool off. And it was. And eventually, again, the Earth more or less formed a solid crust. We know that's not entirely true because I've already introduced the idea of plate tectonics to you guys. So you know there are some giant cracks along this surface. We're going to tell you why those are there in a couple minutes. All right. Homogeneous. No, not homogeneous. How do we say that word? Homogeneous. Good. I still have people say homogeneous, though, so I have to make fun of them. No. We're not making fun of your pronunciation skills, but it is homogeneous. And what does homogeneous mean? What does homogenized mean?
No layering.
Okay. It means all the same. Homo means same or similar. All right? As a prefix. So, when the Earth first accreted, when the Earth first came together, it was homogeneous. That picture you just saw, what does that mean? It means, as he just said, we were not differentiated into layers. There was no crust mantle core. I used the word density separation a couple lectures ago. All right? Density separation is the heavier stuff settles out. The pulp in your orange juice while you shake up your orange juice bottle before you pour yourself a glass of it. While this is cooling off, density separation is occurring. The heavier stuff is settling out. In a sphere, out is down, out is the center. Okay? So the heavier elements, iron, nickel, etc., sank, leaving the lighter elements, silicon and oxygen, etc., closer to the surface. This gave us a layered Earth. This idea is called the homogeneous accretion theory. Longest vocabulary word of the semester so far. Possibly the most letters, I think, for the entire semester. There might be one slightly longer. So homogeneous accretion theory. It might seem like a well, duh moment. We have a lot of those in geology. All right, but somebody had to put forward the idea. I say, hey guys, on day one, everything wasn't all separated out. Now, this could have come about for a number of reasons. One of the easiest reasons that comes to mind is when we were trying to spend a lot of time convincing, when we were trying to convince people that it took a lot of time for the Earth to form. Okay, when we were trying to fight past the 6,000-year-old stuff, and some people are still there. Okay, not my objective in here to make you change 20 years of upbringing. Okay, if you think the Earth is 6,000 years old, that's totally fine. On the test, please answer 4.6 if you want to get it right. That's fine. But this was one of the things. This takes time. Cooling takes time. All those sedimentary rocks take time. How much time? Well, we've jumped 1 billion years, if you didn't notice. Now we're at approximately 3.5 billion years. So, funny thing happens. When things get hot, they expand. When they get cold, they contract. Lots of materials. Not every material, but lots of materials. It's one of the reasons you see these little ba-dump things when you're going over bridges and whatnot. There's these rubber buffery things in there. I had a word in my mouth I wanted to use, but it's gone now. Well, yeah, but I was going to go nicer than expansion joint things that you just said, but yeah. But yes, expansion joints. All right. And what they compensate for is as the bridge, sometimes a little wider, sometimes a little narrower. And it allows, because this material does move, and it doesn't all move equally. The blacktop you're coming off of expands at a different rate from the metal that you're going onto, and so on and so forth. And folks, the engineers in charge of this stuff know all those numbers, so we don't have to. And they take care of that stuff, so we don't have to worry about it. Well, we need to trust then that these guys have those similar numbers for their materials, and they're doing similar things. So if you believe in bridge expansion joints, you ought to believe in this, right? It's a big jump, I know. So at any rate, by 3.5 billion years, as the Earth's crust started to cool, it shrank. Well, the problem is that the inside was still molten. The inside did not shrink. So, in order to compensate for that, some cracks had to form. Next time you're at the grocery store wandering through the produce section, check out an onion. Okay? Just look at an onion skin. It's the exact same idea. Well, it's the exact same outcome. The onion keeps growing. It cracks the skin as it grows, right? In this case, we're going at it backwards, but again, the idea remains the same. There was a brief period of time, I'd like to think, where we were one solid covering. But very soon, okay, there were cracks again. And this is where we have this lovely sort of eruption going on in the background. This is not all volcanic activity is big pointy mountains. A lot of times it's something we call a fissure eruption. The earth just cracks open and bleeds. All right? So this is what's happening here. And we had worldwide volcanism. At this point, it's best to picture something like a baseball or a softball. The stitching going around holding the leather onto it. Okay? So we had these giant cracks open up on the surface of the earth, and lava and gases started to billow out.
I think one of the most frustrating things was when someone blamed climate change on a volcanic eruption that happened.
So, well, it's a half-truth. That's one of those half-truths. There's a hell of a lot of carbon dioxide.
Or no, I meant that climate change caused a volcano.
Oh, caused it. Okay.
The ignorant, bass-backwards one.
Yeah, that is totally bass-backwards. Yeah. But the argument I heard was that one of the senators or congresspersons said, more greenhouse gases come out of a single volcanic event than we make in... maybe, but it's different ones. Volcanoes put out water vapor. Not all greenhouse gases are created equal. And CO2 happens to be particularly bad at causing the problem we're having. Water vapor is a greenhouse gas, but it acts way differently than carbon dioxide does. But we're going to get to that. We actually want some greenhouse gases. We need them to keep us a little warmer than we should have been. So, well, speaking of which, outgassing is our next vocabulary word. So when you picture volcanoes erupting, of course, there's the lava coming down the sides, all right? But there's always that thick, billowing smoke coming out the top, too. We want to talk about that thick, billowing smoke for a moment. There's a lot of different gases released during a volcanic event. By far, water vapor is the number one, all right? And so when you're looking at this thick billowing smoke we see coming out, it's really just water vapor with ash in it. It's dirty water. Now there's some other nasty stuff, don't get me wrong, okay? You've got sulfuric acid, you've got nitrogen, you've got carbon dioxide, you've got all kind of nasties coming out of there as well. But when you see this iconic sort of image like this, the majority of that is water vapor. And I'm stressing that because well, I'll get there in a second. Outgassing gave us our first atmosphere. Our first atmosphere was primarily carbon dioxide, hydrogen, and we got two coming up here. One of them is methane, one of them is ammonia. Which one's which? NH3, CH4. Who remembers? All right, no clue.
NH3 is ammonia.
Ammonia, yeah. Which means CH4 then is the methane. Good. So carbon dioxide, hydrogen gas, ammonia, methane. Sounds pretty alien, doesn't it? Pretty foreign. And water vapor. All right? We can make all of that stuff, or it already exists, I suppose, if you go up and you put a meter on top of a volcano and measure what's coming out of it. All right, those gases are there. Those gases, at least the basic ingredients are there. They combine and make themselves very, very quickly. Some of you are saying, oh, wait a minute. I remember it wasn't that many lectures ago, you said that we have an atmosphere because of gravity, and we have a gravity because of our mass, and damn it all, we've had the same mass since first day. Why didn't we have an atmosphere before this? I know at least half of you were thinking that. Sure. Smile and nod. All right. Simple reason. So they tell us, at any rate. It was too hot. It boiled off. All right, remember we were that fiery gaseous ball of goo until the majority of the surface. Yes, worldwide volcanism was going on, but again, picture that softball. It's focused. You've got these fissures that are opening and billowing stuff out. The protoplates, if you would. Protoplate boundaries, really. The majority of the Earth, the ambient surface temperature, is a lot cooler now. So those gases don't just immediately boil away. They're allowed to build up, they're allowed to accumulate because of the Earth's gravity keeping them there, okay? Yes, we've always had a gravity, and yes, the same stuff that's billowing out of this volcano obviously was in the magma or the lava when we were a fiery molten ball of goo. I'm with you on that one. I totally get it. But it was too hot, it just boiled away. Now that things are significantly cooler, it can build up. Anywho, one thing conspicuously missing here is oxygen, what we call free O2 or breathable oxygen, okay? There's oxygen in the carbon dioxide there, there's oxygen in the water vapor, but nothing that you can breathe. We'll get there. So as I started to say, we really want to push that emphasis on the water vapor there because we want to build not just an atmosphere, but an atmosphere that you guys, squirrel, hey squirrel, an atmosphere that you guys know and love, all right? with clouds, with weather, with eventually squirrels running around in it. So, as we built up an atmosphere, as this worldwide volcanism started to wind down, things started to change at the surface. Just like nowadays, that water vapor rises up. We haven't talked about the water cycle in this class yet, but you've heard it before. All right. The water vapor higher up in the atmosphere cools off. When it cools off, it changes from vapor to liquid. All right. The ash that's coming out of these eruptions serve as wonderful, just throwing another vocabulary word at you, I apologize, you don't need to necessarily remember it, condensation nuclei, little kernels that get things started. Water vapor loves to stick to itself, but it often needs a little something, okay? That's why acid rain forms so easily, unfortunately, and a handful of other things. We get all those particles coming out of smokestacks floating around, and the water vapor just goes like magnets to it. So, we've got all this ash floating around in the atmosphere, and the water vapor clings to that. And little by little, bit by bit, we started to form clouds. And when clouds get big enough, as you know, they start to fall apart. What we call precipitation, rain. This one's a tough one, even for me. How long did it rain? Hell of a long time. Well beyond 40 days and 40 nights. Okay? It rained and rained and rained and rained. How long did it rain? It rained to fill up the oceans. It's where they came from. Now, there's one alternate hypothesis we're going to talk about, and it's definitely credible, but it's not enough of a reason to be the primary source. So when I ask you on the test, which I will, what is the primary source of the Earth's water? The answer is outgassing. Okay? And from this primary event. Our water is very, very, very old. So you can't put a number on this. I sure as heck can't. But we do know that for the most part, before this event, we did not have water puddling up at the surface. After this event, and this is an ongoing process, don't get me wrong, but after this event, we had some semblance of the oceans. Now, as I said, there is a secondary option here. We talked about comets briefly several moments ago. Comets, as you know, they call them dusty snowballs, right? They're ice and a whole bunch of galactic riffraff, solar system riffraff. And undoubtedly, some of them smashed into the Earth. We have an atmosphere, we have weather, we have all kinds of stuff going on. And because of that, we don't see a whole lot of craters on this planet. That's why that one that I showed you a little while ago is so special. But if you've ever looked up at the moon, you see all those craters on the moon. The moon is a fraction of our size. All right? And again, even if you're not into shooting sports or whatever, you know, the smaller something is, the harder it is to hit, right? Well, we had to have gotten hit at least as many times as the moon did. Not all comets. Again, there's some asteroids smashing into us and whatnot, but you get my point. I totally agree with these guys. We definitely got hit by some comets. Those comets came, they melted, they left some water. It's a lot. You need a lot of comets. And here's the thing. We have since landed on a comet. It's been a while. We got a sample of their water. There is a different, I'm going to use a word isotope. It's not quite the right word for it, but there is a different kind of water that comes from comets. We can recognize it because, again, we landed a probe on it and sampled it and sent it back. And we see that in our oceans. It's there. But the ratio is way, way off. So until something better comes along, okay, comedic water is a Great secondary source, no question about it, but it is far from a primary source. Now, if somebody could come along and proves that it decays into what we call earth water, well, then we got a whole other conversation opened up. But to my knowledge, no one's working on that one, so it's probably not a thing. I know decay happens, and I'm saying, why doesn't it happen with that? But again, I'm done going to grad school. You guys could take that one up. And we continue every day to get bombarded, not by, thank God, giant things like this. That is a nice part of the process. It's sort of a self-eliminating process, right? As when an asteroid or a comet smashes into something, it kind of removes itself from the equation, as it were. There was a period, again looking at the moon, called period of heavy bombardment. We got hit a way lot more than happens nowadays. But there is a constant downfall of little, pixie dust kind of stuff. All right? So even though they tell you the water cycle is a closed system, we still get a little bit more here and there. While that's going on, I used to, those chronology things, put these in the right order. I used to have my test question that way. And it was a way of dealing with, it was a way of first of getting off of an essay question, a short answer question. Explain what happened from when the Earth solidified to when we had an atmosphere. And people did horrible on that, of course. So then I said, okay, well, let's give you guys all the important vocabulary words. You put them in the right order. They actually did worse on that. And it took me a little while to figure that out. Well, how could they do worse when you give them all the vocabulary words? And I came to realize that there's just a lot of stuff going on all at once, which I knew, but the subtleties are not at a 101 level. In other words, you have to have something before something else can actually happen, okay, like for this photochemical dissociation that we're going to go into. You had to have a step or two before that, or this couldn't happen. And yeah, I realize that's the point of chronologies, but you guys aren't geology majors. You aren't even, sophomores or juniors. So I split it into a whole bunch of separate questions, and that's why, we don't get very high up Bloom's taxonomy with the tests these days, and I feel a little bad about that. But this is some pretty heavy stuff when you try to blend it all together into a cohesive idea. All right, and I'm presented to you that way, but I realize in the end you're probably going to come out of here with, a string of vocabulary words. I'm more than happy to talk with any of you more in depth about this stuff, okay, at any point in time. But yeah, I do try to give it to you in a logical order. But I understand there's a lot of stuff going on at the same time. So, while it's making volcanoes and making an atmosphere, clouds are forming, it's raining, the oceans are filling up, comets are falling on us, and, oh, by the way, photochemical dissociation is going on. And then 3 other things after we finish this vocabulary word. So, and we're at 3.5 billion years ago. You caught up? Great. So what is photochemical dissociation other than only slightly shorter than homogeneous accretion theory? This is how we got our friend ozone. All right, remember, we like ozone. So sunlight plus water vapor equals oxygen and hydrogens. So I'm saying that sunlight splits up water vapor? Yes, exactly what they're saying. That's the dissociation part of it. Photochemical. Photo means light, not picture. Chemical, well, that's just chemical. So light, chemical, split apart. Even if you forget this word by the time we get to the test, just break it down into what it means and find an answer that fits it. So water vapor, in the presence of sunlight, will break into its components, hydrogens and oxygens. Yes, that's going on out there right now because the sun is shining and there's water vapor in the air. It's always going on. and we have to fit it into this early puzzle. Why it's important is because those O2s can make O3, which is ozone. Now, every so often, again, if you've lived in or around a big city, you might have heard of like ozone awareness days and so on and so forth. That's smog. Okay, smog is ozone, slightly different way that it's formed, but if you've ever been to LA or Manhattan and you get that sort of taste in the back of your throat, that is ozone. All right? Ish. But we need it up in the, what level does it live in? Yeah, the stratosphere. Not the troposphere where we live, but the stratosphere, the level above us. We like our ozone there. It makes the ozone layer. And the ozone layer filters what out for us? Yeah, ultraviolet radiation. Beautiful. All right. So at some point, we had enough photochemical dissociation happening that this ozone layer built up. It too had to grow. It wasn't a magic wand, poof, there's a layer. Okay? Now I say that a lot, but some things like the magnetosphere, that was probably just a turn on, turn off kind of thing. Once we start spinning, you've got the shield. But this other stuff had to build up. It took time. So again, going back to everything's the same age, everything, that's pretty relative. Okay? But compared to the other stuff that's going on around us, safe to say they're the same age. Okay, let's go back down to the earth for a moment, get out of the sky. So remember I told you that all that ash was mixed in, right? It wasn't just water. There's a whole bunch of ash in there as well. What time do we go to? 9:25? Oh, hell, I got plenty of time then. Okay, good. I was getting nervous. I think it is too, now that you say that. For some reason I was thinking it was like 10. 9:10 or something. So ash. All right, we haven't had a whole lot of geologizing going on yet, but you do realize that the earth is made up of elements. Elements make minerals, right? Minerals make rocks. So ash, at the very least, is a whole bunch of elements. And that is dissolved into this rain. Remember we talked about how easily acid rain forms? Well, this isn't acid rain. I'd like to call this water plus. Okay, that fancy water you guys go and pay a couple dollars a bottle for nowadays. It's pH balanced, it's in electrolytes, it's enriched, it's this and that. Nature was doing that 3 billion years ago. Well, you got lots of interesting things in the water now. Like plastic. I don't know that we have plastic in the atmosphere yet. That might be one place that is still plastic free. But we'll see. I bet microplastics can float around in the atmosphere. Oh, good Lord. That's for my environmental science class. They'll talk about that one. So, of the many things that we need at the moment, you remember we had methane, we had ammonia, we had water vapor. We need carbon, hydrogen, oxygen, and nitrogen. The unfortunately coined term chone. This doesn't sound good. Chone. All right? And those are the basic ingredients for life as we know it. You always got to put that obligatory thing on the end there. Those are the main ingredients for life. Carbon, hydrogen, oxygen, and nitrogen. It's what we need. It was all there. All right. Now, we're moving on to something called the organic soup theory. This is not down the crunchy nutty aisle of Hannaford's or going over to Pete's or anything like that. This is organic soup in that we are working on making organic materials on the planet. A couple of guys right around your guys' age, back in 1952, going on 75 plus years ago now, I believe, if I just did some quick math there, put together this interesting contraption full of Erlenmeyer flasks, tubes, and beakers and whatnots. And they put in these components that we just talked about. They put in some salt water. They put in some carbon, some hydrogen, some oxygen, some nitrogen. They made a little atmosphere above this salt water. And they put one thing that we need to get most everything started, a little energy. They put in a bit of a spark, lightning. And they let it sit, cook if you would. And they came back and they had some brown goo. And then they did it again to make sure someone wasn't messing with them. And they got brown goo. And they did it again and again and again. Now, they did not create life. I'm not trying to convince you that they created life. But they did make the necessary components, arguably the precursors for life. They made amino acids, proteins, sugars, stuff like that. They didn't make them. They made themselves. In a very controlled situation, but that simulation was meant to mimic a potential early Earth situation. They showed that these things could form. Now, talk about it's not for this class. It is not for this class. Historical 102 geology. We used to talk about this stuff a good bit. How we get from this to pond scum. All right. And again, I don't know that we'll ever know how that is. There's lots of ideas out there, and we have a good time talking about the potential possibilities. But right around 3.5 billion years, again, more or less right where we were on our time scale here, in the rocks we find fossils of bacteria. So again, it's not necessarily a throw it out because we don't know how we got from amino acids to bacteria, but let's figure out how we got from amino acids to bacteria, because we know we could get amino acids and proteins, and we know we ended up with bacteria, not to mention all the other crap that came after the bacteria. So let's focus on how that maybe could have happened. And again, that is a whole nother semester's worth of conversations. So we're just throwing that out there. So at approximately 3.5 billion years in the rock record, we see the development of the first living creatures on the planet. Yes, bacteria are creatures by a stretch. Okay, we're all familiar with plankton and his ornery little funny self. We're before plankton even. But bacteria are single-celled organisms. That's why you can have an antibiotic for bacteria. You ever notice they say, oh, you got a virus, it can't do anything for you. Viruses aren't alive. You can't kill them. But bacteria are alive. And we have things to kill them. They're working on antivirals. They're coming, But the bacteria is alive. And again, it's certainly not fuzzy little bunnies and grass and trees and all that stuff. But it is the first organism that we have a record of. Now, you guys may have heard algae. Okay. Blue-green algae. Very common, very popular. But it is indeed bacteria, blue-green bacteria, or cyano. Cyan is that shade of blue bacteria. And as always, I have a funny little side story. So back before I had kids, or right when I still just maybe had one very young kid, I used to be able to go to conferences and disappear, and my wife would enjoy the time by herself and so on and so forth. So I went to one in whatever college is in Springfield, Mass over there. And it was probably a science teachers conference. It might have been Geological Society of America one, I don't know. And so we went around, to all our various talks during the day. You pick stuff that you want to hear about, so on and so forth. And they always end with this big dinner. You get a piece of chicken cordon bleu, some dry rice, and you listen to somebody talk, and they charge you $50 for it, and so on and so forth. So I didn't sign up for that. I was still an adjunct teacher. I didn't have any money or anything like that. So it was enough just to go to the conference. But these people I'd been walking around with, they're like, oh, you got to stay. It's one of our teachers. Well, she's retired, but she was one of our teachers. She's really cool. You got to stay. and you like that fossil-y stuff and all that, you should stay. I'm like, okay, fine. So I got myself a last-minute ticket, or I snuck in, I don't remember which. And so I'm sitting with these guys and a couple, like, adults. I was still, early 20s, so I didn't consider myself an adult yet. And this little old lady, like with a shawl and everything, just sitting there. And I was actually sitting next to her. So we're doing our thing, and it's time, for the guest speaker to get up. And oh my gosh, her name just jumped out of my head. So it's also like talking to your grandpa, right? This is all this story. And who the hell was it? I forget now. So they call up the guest speaker, and this little grandma sitting next to me gets up and goes up to the stage and starts talking. Lynn Margalis. There we go. I remember it now. Dr. Lynn Margalis, everyone. And this, like I said, this little grandma goes up to the stage and starts talking about crawling through the sewers of France. I'm like, what is this? What is she talking about? So she studied this stuff. And this was, again, a good, decade or so past. This has been a while. And in the end, she's like, okay, you guys I think it must have been a science teacher conference. She's like, so you guys, when you go out there, please stop using the word algae. Okay, it is not blue-green algae. It is blue-green bacteria. And we need to get people to stop calling it. This is right when, again, I don't know if you guys, how much biology you remember, but when we started with the kingdom Archaea, and they split all the bacteria. It used to be Monera. Again, a whole bunch of stuff if you did learn, you probably didn't care too much about, because no science majors here, right? Science major, yeah. So, all right. So, anyway, this is when all that was happening, and to this day, I still carry her message. All right. And also, never judge little old ladies. All right, they were who may have crawled through the sewer just to get there. But no, she turns out she was like hanging with Carl Sagan and all those guys. If you guys heard about Gaia, okay, the Gaia hypothesis, James Lovelock, that was her crew. And I was just like, oh wow, this is wild stuff. So all these people I'd grown up knowing about and hearing about, and here I was sitting with one of them. I didn't even know it. So neat stuff, but it is bacteria. All right, and bacteria. Back to the point, blue-green, there's stuff going on there. If you know about this, you might remember. What is it that we like green? Green does what? In plants and all this stuff. Green is good because, why? Yeah, sorry. Jumped ahead of myself. And what does photosynthesis? What little organelle? Push in your memory banks. Help her out, folks. You're very close. What? Chloroplasts. Chlorophyll is in chloroplasts, right. So chloroplasts are the organelle. They're blue-green because they've got chlorophyll in them. They've got chloroplasts in them, which means they're a compound organism, which should impress you at this point. All right? They're very complex. Again, relatively speaking. So there's a lot going on there. That means that there was stuff before them. They just didn't fossilize and so on and so forth. So what did we find? What are these fossils? So these fossils are called stromatolites. And the stromatolites are essentially condos or apartment buildings. I'm going to show you a picture of one in a moment. This is one sideways. If you're wondering why I bothered to turn it sideways, it's so I could still keep it big enough for you to see those layers. So if you've ever walked through a stream, slipped on some algae, in air quotes, you folks at home can't see me doing that, and cursed at the stream or the rock, you've come across blue-green bacteria. And sometimes it is algae, don't get me wrong, but a lot of it is this stuff. It grows on rocks. And even though you just slipped on it, believe it or not, it's actually kind of sticky because it's filamentous. It's got all kind of little fuzzy little hairs on it. Those fuzzy little hairs are really great, not just at making people slip, but at capturing mud, which promptly kills them. And then more bacteria grows in on top of that. They get covered up in mud, more bacteria. You end up with a layer cake. Okay, again, over thousands and thousands of years this takes place. All right, as long as you don't have hikers, scratching it off with their big old clumpy boots. So this represents a fossilized version of that. We found these things. They didn't know what they were. It took finding someone who studied these things to bump into someone who found those things and said, wow, that looks like a cross-section of my stromatolite. And they're like, so what now? And this is before we had Google. And they put 2 and 2 together, and for once they didn't get 5, they got 4. We still have stromatolites, all right? And because we have stromatolites, we could look back and see that, oh my gosh, these things we find in the fossil record, they are those. We can assume, safe assumption, that the way they form now, where they live now, also is how they lived and formed back when we found these. So they sorted it all out. So a stromatolite is not the bacteria. I just want to reinforce that. Okay, it is the structure that they form or grow as they build up on rock over time. That's why it was curved. See the curves in there? That's just the surface of the rock that it was growing on. So they form in shallow water. Again, they are chlorophyll things, so we don't see them in too deep of water. So now we're actually starting to build an environment. All right, we have these organisms growing on rocks in water, in shallow water, more than likely near a shore, and hopefully you're starting to get a picture in your head, and that's exactly what we were going for here. We're reconstructing this environment. Even though it's 3.5 billion years old, we're starting to get an idea of what it could have looked like. So back to the green stuff. Not going to make you memorize the photosynthesis formula. You know there is one though, right? Okay. So you know that the end product of photosynthesis is that carbon dioxide is converted into sugar and oxygen. Sometimes I attempt to rattle off the formula, but I'm not even gonna. I'm a little too foggy today to do that. Where did the carbon dioxide come from? There's some in the atmosphere, but okay. We got some in the atmosphere. We've also got some from the bacteria. Bacteria love the sugar. So the chlorophyll gets fed by the bacteria. The chlorophyll then feed the bacteria some sugar. Nobody wants the oxygen. Chlorophyll doesn't want the oxygen. The bacteria doesn't want the oxygen. So it's expelled. It's waste. We don't go straight to the atmosphere, though. We first have to oxygenate the water. They say that the oceans were first green because of all the iron in them. Now, I associate green with copper, right? But they tell us that the oceans were green first because of all the iron in them. What happens when you mix iron and oxygen? You get iron oxide, right? And you get rust. Yeah. This is out of place. There we go. We're not changing our atmosphere yet. That's weird. That slide shouldn't be in that order. All of the majority of the iron that was in the water, once that oxygen from these bacteria bonded with them, it deposited, came out of solution, and made what we call banded iron formations. In other words, this again is a process. It builds up. So you hit a saturation level, you get a deposit. This is some chemistry talk. I apologize. And then it takes time for that to build up. In that time period, sedimentation is happening. So just like you've got mud on top of your stromatolites, and your stromatolites on top of the bacteria there, we've got a period of mud, and then boom, we get another deposit of iron. So that's the banded part of the iron formation. They're very cool looking. All right. If you ever get to Manhattan and you're bored go to the, it's not exactly Upper West Side, but mid to Upper West Side of the American Museum of Natural History. They've got a beautiful slab of this. It's right off Central Park. Okay, it's free. They're going to ask you for $35. Just say, I've got $1. Thank you. And they have to let you in. Unless that gets changed with new legislation. They have to let you in. After 9/11, they changed their whole thing. They just had baskets and you'd toss in what you had. But now they got to keep tabs on everybody who enters. So they want money, but they will let you in for whatever you have in your pocket. Anyhow, go look at the cool dinosaurs. Go look at the giant blue whale. Go look at all that stuff. But make sure you walk through the rock and minerals and see this giant slab of iron. They say that this event, okay, when we oxygenated the water for the first time, is where we got all the iron that we're still mining today. It was pulled out of solution, deposited, and we're mining it. It's banded iron formations. I am almost done, you guys. This is super, super long. I appreciate you staying with me. I got 3 minutes left, and lo and behold, we're back to talking about the atmosphere. So we're winding down. Once we oxygenated the water, it was free to bubble out. And slowly but surely, oxygen began to fill up the atmosphere. As you know, it's still not, it's not like a major component. It only had to get up to 26%, was it? 21%? 22? Thank you. Yeah, I'm looking, we're barely over the 20 there, so it's not 26. 22%. We didn't have to get that high. But it did grow, okay? It went from 0 or very low to that. Here's our actual. I got 21 on this one, but I'm not going to argue with your 22. Until we arrived at our current atmosphere. Now, that was a lot of stuff. A lot of vocabulary words. And a lot of it relatively new to many of you. When you sit down to worry about this for our first test, which is coming soon, all right, we want you to look at the PowerPoints. Focus on the vocabulary words. Because as I said, I'm not going to necessarily ask you to put this together in make one big puzzle out of it. Okay? That comes a little later. Right now we need to master the vocabulary words first. First tests are important. All right? And so I want you to do good on them, and the way you're going to do that is by focusing on the vocabulary words and the PowerPoints. So, all right, you guys, we've got another lecture when we come back. So the test isn't like next, but it is coming soon.